So I, I agreed to give this talk. So I've prepared the talk over the last few weeks, and I realized there's a lot of material to cover, because to really survey explanation, I have to talk about causality, and I have a talk that's easily an hour on causality. So, fasten your seatbelts, ask questions as we go along, and I'll try to give you a sense of what's going on with explanation, at least from my perspective. So look, defining explanation is hard. People have been trying for millennia. And just as in the work on causality, what happens is that people propose a definition, and then the philosophers all get to work and try to shoot down the definition. So, ideally, as Nico mentioned, my PhD is in math. I'd love to prove a theorem that said, right, I have the right definition. This is a theorem. If I only knew what the theorem ought to say, because, how do you formalize the idea that the definition is right? Then, maybe I could try to prove the theorem, but I don't even know how to state the theorem. So I guess what I'm going to do is, just as in the work on causality, I'll be giving you a definition and arguing by example and intuition that it's a reasonable definition. But the trouble with that argument is that, tomorrow or today, somebody could come along, maybe after hearing this talk, and say, well, here's a counterexample. Your definition doesn't work quite right. And it's true, that could happen. And I will say that the definition I'm going to give you here is not the first or second, or probably not even the third, fourth, or fifth definition I thought of. It's not the one, it's based on the definition in a paper that Halpern and I wrote, but it's not the same. It's actually the definition that's in my book on actual causality. But the fact that I went through so many candidates before I found this one, it really was, looking at the examples and saying, oh, that one doesn't deal with this example. Let me patch it up to get it to work on that example. And it does leave me open to the possibility of other counterexamples. But the intuition, which I think will hold up, is that a fact is an explanation. If it were found to be true, it would constitute a cause of what philosophers call the explanandum, the thing you're trying to explain, regardless of the agent's initial uncertainty. So let me try to unpack that and explain it. So just a little bit of history. There's a ton of work on explanation. In the 20th century, the big names are probably Hempel and Salmon, Carl Hempel and Wesley Salmon. And Hempel considered two types of explanations, what he called deductive nomological and inductive statistical. And they both had the same spirit, that an explanation consists of a set of facts, initial conditions, in the deductive case from which the explanandum, remember that's the thing you're trying to explain, logically follows. So I'm going to give you a bunch of facts, and once you accept those, then so these are facts that are true about the world, and therefore the thing I'm trying to explain follows. And in the inductive statistical version, the facts are not actually necessarily true facts about the world. I mean, Hempel talked about laws. They're just statistical statements that are typically true. But, philosophers got to work on lots of counterexamples to this definition, that we certainly wouldn't think of the barometer falling rapidly as being an explanation of the storm approaching. The two events are closely correlated, but the barometer didn't cause the storm. It's just correlated with the storm. And because it didn't cause the storm, we wouldn't accept it as an explanation of the fact that there's a storm. Now, another issue raised by von Frassen and Peter Jerdenforsch is that the explanation must raise the they talked about the explanation raising the probability of the explanandum. That again, it's an explanation if it makes the thing you're trying to explain more likely. But they too had this problem that they didn't take causality into account. So telling me the barometer is falling does raise the probability of a storm. It does, but we don't take it to be an explanation. But there is an issue raised by von Frassen and Jerdenforsch that I think is quite correct, and that's the issue of knowledge. So what counts as an explanation for one person might not count as an explanation for another. This is something that Bas von Frassen pointed out. And here's an example of that due to Jerdenforsch. So suppose that we seek an explanation why Mr. Johansson has been taken ill with lung cancer. So here are two possible explanations, and they both seem reasonable. That he worked for years in asbestos manufacturing, that's explanation one. And another explanation is that you describe the causal connection between asbestos fibers and lung cancer. So if you don't know that he worked for years, that Mr. Johansson worked for years in the asbestos mines, but you do know that asbestos causes cancer, that's B. So if you don't know A, but you know B, then if you don't know A, but you know B, then A is a good explanation. Conversely, if you know A, that he worked for years in asbestos manufacturing, but maybe before you had no clue that asbestos fibers cause cancer, then B becomes a good explanation. So what counts as a good explanation depends on what you know already. So in the intuition is that the explanation is so to speak, filling in the gaps of your knowledge, right? So that different people know different things. So what will fill in the gaps of the knowledge will vary by the person. And so we want to take that into account in our definition of what counts as a good explanation. And the other thing I want to point out, because I'll come back to it later, is that a fragment of a causal model might be part of an explanation. So describing the causal connection between asbestos and lung cancer really might be part of an explanation. And that really can be thought of as part of a causal model. So let me, for the next 5 or 6 slides, I know it's supposed to be a talk and explanation, but I'm afraid you're going to get a talk in causality, at least for a little while, because I can't explain explanation without explaining causality. So let me jump. I'll skip a lot of the motivation intuition that I would normally give if I was giving a talk purely on causality, just in the interest of time. I'm hoping you've seen some of it in other papers and talks, but here's the formal model that I'm going to use. So a model consists of, think of a Bayesian network. So I have a bunch of variables. They're the variables in U and V. And if you think of a Bayesian network, and I'll come back to this, the variables in U I call exogenous variables. This is actually Pearl calling them exogenous variables. This is his notation. Think of them as the variables at the root of the Bayesian network. Intuitively, these are variables that their values are provided by the world. You're not going to try to explain why they have the values they do. Why do people like throwing stones at bottles and shattering them? Well, I don't know. That's determined by an exogenous variable. Now, the endogenous variables are the variables, if I think of a Bayesian network, that are not at the root. And their values are going to be given by what are called structural equations. That's the F. And there's a structural equation for each endogenous variable. So for each variable that's not at the root of the Bayesian network. And the equation gives you the value of the variable as a function of the value of its parents. So I might say the equation might say x equals y and z. So that will tell me the value of x as a function of the value of y and z. So although I have an equal sign here, you should think of it as more of an assignment statement. This tells me if I were to intervene and set y to false, then x would be false, right? That's how you should think about these equations. They tell you the results of interventions. So a variable x depends on a variable y if y can affect the value of x. So intuitively, if y is a parent of x. And I'm going to assume, in all of this language, I've assumed that the depends on relation is acyclic, so I can really model what's going on using an acyclic network like a Bayesian network. I have models, in my book, I talk about cases where we have cyclic models, but for the purposes of this talk, let's assume that the models are acyclic, so they really are like Bayesian networks. And again, in this case, the exogenous variables are the roots of the Bayesian network. There are the nodes that don't have parents. And so with a Bayesian network, we would associate with each node X a conditional probability table. I'm assuming all of you know Bayesian networks. So the conditional probability table will tell you the probability of X as a function of which of its parents are true. And here, rather than a conditional probability table, we have an equation that shows how the value of X is determined by the value of its parents. So like a Bayesian network, except replace conditional probability tables by functions, and that the functions are exactly this F. So that's a causal model. And just a teeny bit of logic. This is all the logic you're going to see. I just need some definitions. So let U be a context that's just a setting of the exogenous variables. It tells you, again, if you think of this as a DAG, it tells you the value of the nodes at the top. And since we have equations for all the other nodes, once you tell me the values of the exogenous variables, and that's exactly what a context does, that determines the values of all the other variables, because I have equations that determine all the variables further down the DAG. So I'm going to say that the value y equals 3 in model M, and remember, a model is just this tuple with equations and exogenous and endogenous variables. Given a model and the context again is a setting of the exogenous variables, I can tell whether or not y equals 3, because that determines all the values of the variables down the DAG. And I'll write the formula y equals 3 is true given a model M and context U if y equals y, little y is indeed the unique solution to equations once, when I say in U, I mean once I determine the values of the exogenous variables. Now here's the interesting formula, and I'll just be using this formula in a number of places so you need to understand it. The way to interpret this, you can almost think of x gets little x as a modal operator for those of you familiar with modal logic. This is saying if I were to intervene and set x to 3, what would phi be? Would phi be true or false? So I have these little arrows over the x because x can be a vector of variables. So really you should think of this, if I were to intervene and set x1 to 2 and x2 to 5 and x3 to 7, then phi is true. That's what this is saying. If I intervene and set capital X to little x, then phi is true. And that formula is true in this model, given this context, if the formula phi is true in this new model. Now, what's this new model? It's M sub x gets little x, same context. So this is a new model, which is just like the original model M, except I've changed the equations F. Remember, a model is a triple with variables and equations. I've changed the equations for the variables X by just saying whatever the equation was before, throw it away. So if this were just x gets 3, I now replace the equation for x and just say the equation is now x equals 3. So intervening on x by setting it to little x just means throw out whatever equation you had for x that no longer applies. I'm, so to speak, overriding the equation and replacing it by the equation x gets little x. Think of little x as 3. I hope that makes sense. That's the semantics of this formula. And let me just give you some examples. And those of you who heard me give talks on causality will have seen these before. I apologize. But I will come back to this in the context of explanation, and things work a bit differently there. So 2 arsonist droplet matches in different parts of a dry forest. And in both cases, that causes trees to start burning. And I imagine 2 scenarios. One I'll call the disjunctive scenario, where either match by itself is enough to burn down the forest. And in the conjunctive scenario, you need both matches to burn down the forest. So here's how we would model it. We would have an exogenous variable that determines whether or not these arsonists drop their matches. I'm not really concerned about what makes them drop their matches, so it's determined by some exogenous variable. And whether or not there's a forest fire depends on whether the arsonists drop their matches. And in particular, in the disjunctive scenario, I have this equation that says there's a forest fire if either arsonist dropped a match. So ML1 and ML2 are 2 variables. Well, here it is, MLI equals 1 if arsonist I drops a match. So I'm going to say in the disjunctive model, the equation for FB is just the disjunction. The forest burns down if either one drops a match. That's this. And in the conjunctive scenario, it's just replacing the or by an and. It says that the forest burns down if both of them drop a match. And in causality, we want to say, what does it mean to say that A is a cause of B? And I won't go into great detail here, but I'll try to give you the intuition because I'm going to need it for the explanation part, which I really am getting to. So I'm going to talk about A being a cause of B in a model. Whether or not A is a cause of B depends on the model and the context. And remember, the context is a setting of the exogenous variables. So I'm going to restrict the things that are causes to just conjunctions of basic events. So I can say x1 equals 2 and x3 equals 5 caused phi to happen. The phi can be an arbitrary formula. So the intuition is, this is what lawyers call but-for causality, that A is a cause if, had A not happened, B wouldn't have happened. Me dropping the match is a cause of the forest fire Had I not dropped the match, there wouldn't have been a forest fire, right? Me punching you in the nose is a cause of you falling over. If I hadn't punched you, you wouldn't have fallen over, right? So this is what the law calls a but-for cause. But for A, B would not have happened. But, you know, that's a good intuition, and that works in a lot of cases. That's sort of the simple setting. Unfortunately, there's lots of real-world examples that show that this doesn't work. So here's an example due to David Lewis, who's a very well-known philosopher. Susie and Billy both pick up rocks and throw them at a bottle. Susie's rock gets there first. Maybe Susie throws a bit harder, or she throws a millisecond earlier. So her rock hits the bottle, it shatters the bottle. And now you can see that Billy's rock sails over where the bottle would have been had Susie's throw not shattered it. But nevertheless, so both shot throws are perfectly accurate, you can see, and Billy's throw would certainly have shattered the bottle if Susie's throw hadn't gotten there first and shattered it before Billy's. So I think in natural language, most people would say Susie's throw is a cause of the bottle shattering, Billy's is not. But had Susie not thrown, then Billy's throw would have shattered the bottle. So the simple counterfactual doesn't work. Susie is not a but-for cause of the bottle shattering. It's not the case that but for Susie's throw, the bottle wouldn't have shattered. It would have shattered anyway because of Billy's throw. Right now, you could say it would have shattered a millisecond later, but so it's true that Susie's throw is maybe a but-for cause of the bottle shattering exactly 9:13. Had she not thrown, it would have shattered at 9:13.01 or something like that. But that's not what we say in natural language. And by the time you start thinking of these milliseconds, then you have to allow things like the gust of wind as being a cause of the bottle shattering, or the lack of a gust of wind, because had there been a gust of wind, it would have shattered a millisecond earlier. So I really am interested in what's the cause of the bottle shattering, not what's the cause of the bottle shattering at exactly 1 millisecond after 9:13. So the definition that we gave is that x equals 3 is an actual cause of phi. So, you know, Susie throwing is a cause of the bottle shattering. Well, the first condition is quite non-controversial. We wouldn't say that Susie throwing is a cause of the bottle shattering unless it's the case that both Susie threw and the bottle shattered. So unless it's the case that both x equals x and phi are true in the world, we wouldn't call x equal x a cause of phi. Then there's a really complicated condition, which got simpler over the years because I have 3 papers that give definitions of actual causality. The reason I have the 3, well, the first one looked like a good definition until, this is joint with Uta Pearl, until one of Uta's students, Mark Hopkins, found a counterexample. Exactly what I said, you know, I can't show that there's no counterexample. Well, he found one. So we fixed up our first definition to get a second one. And then years later, I came up with a third one that I actually prefer, not because there was a counterexample, but so I'm giving you the third definition here. So all 3 definitions had the same basic format, that there was an AC1 that had said this. There was an AC3 that was a minimality condition that said, I'm never going to call x1 equals 1 and x2 equals 2 a cause if x1 equals 1 is already a cause. So I don't have any irrelevant conjuncts here, right? I don't want to say that dropping a match and sneezing is a cause of the forest fire if dropping a match by itself is, right? So AC3 is a minimality condition. Again, this is quite non-controversial. AC1 is also non-controversial. All the action happens in AC2. I'm going to give you AC2 on the next slide. It is a little complicated, but all I can say is this is, you know, AC2 version 3, or at least published version 3. There were versions 4, 5, 6, 7, and 8 that never got published. And version 3 is simpler than versions 1 and 2. It's the one I wrote in a paper in 2015, I think. So here's the condition. Now, just ignore this W gets W for a second. So ignore that and look at the definition. It says, so forget there's a set of variables in V in a setting. So there's a setting x prime of the variable x such that, again, forget this part. If I set x to x prime, phi doesn't happen. This is the counterfactual. So ignoring the W, if W was the empty set, if that W wasn't there, this would just say x equals 3 is a cause of phi. If there's some other setting of x, you know, if x weren't 3, then phi wouldn't happen. So if x were x prime rather than x, phi wouldn't happen. So that's the but for, and this is the, so with the W it now becomes an extension of the but for. The but for is the special case where the set W is empty. But in general, I'm willing to allow you to fix the values of a bunch of variables at their actual value. So fix them when I say their actual value, the value they have in the real world. That's just this saying mu satisfies W equals W. So I'm fixing it at W equals W. Now, why do I need to fix it? That's because setting X to X prime might change the values of W. We'll see this in an example. But if we clamp W down, keep it fixed, despite the fact that we change X to X prime, and then phi doesn't happen, then I will say that X being X is a cause of phi, because if X weren't X, counterfactually, and also if you kept W fixed at little w, then phi wouldn't happen. So that's the condition, and let's just look at a few simple examples, and then I'll get to explanation, I promise. I mean, it's coming. So each of ML1 and ML2 is a cause of the forest burning down the conjunctive scenario. That's easy to see. If you need both matches to get the forest to burn down, if either arsonist hadn't dropped a match, but for the arsonist dropping a match, we wouldn't have the forest burning down. So each of them is about for cause. This shows you can have more than one cause. They're each separately causes. Now, in the disjunctive case, the way the definition works is it says the conjunction is a cause because you need to change both of them to get the but for condition. If you change, since either one of them being one is enough for the forest to burn down, to get the forest not to burn down, you need them both to be 0. Now, arguably, natural language doesn't work like this, but I'm going to come back to this point when I define sufficient causality, and that's coming up when I talk about explanation, so stay tuned. Let me just briefly look at the Susie and Billy example. So here, this shows the importance of the model. So if we just have a model where the only variables are Susie throws and Billy throws and the bottle shatters, then in this model, Susie and Billy are completely symmetric. And each of them is a cause of the bottle shattering. This is just like this disjunctive example, the disjunctive forest fire case, where one match is enough to get the forest to burn down. If the equation for BS is the bottle shatters if either one of them throws, so I'm sort of baking into the equation the fact that they never miss, they're perfect shots, then it really is the case that BS is ST or BT, just like the disjunctive forest fire case, where the forest burning down was the disjunction of ML1 and ML2. And indeed, they're both causes. And I claim this is just a bad model of the story because it's missing out. I mean, nowhere in this model am I capturing the fact that Susie's throw hit the bottle first. And here is a model that does capture that. It's not unique. There are many other models. They all have the same outcome. But suppose I added a variable that said Susie hit the bottle and Billy hit the bottle. So two more variables. Now, if Susie throws, I'm going to have the equation say Susie throws, then Susie hits, she never misses. But I'm going to bake into this model, I don't have to, I could have a more general family of models, but let's say I bake into this model the fact that Billy only hits, well, he has to throw in order to hit, but Susie threw first. So if Susie throws and Susie hits, then Billy doesn't hit. So the equation for BH is Billy throws and Susie doesn't hit. That's the equation. And again, the equation for the bottle shattering is either Susie hits or Billy hits. So in this model, where we're modeling the fact that Susie's rock hit first, and therefore Billy's rock doesn't hit if Susie hits. So if Susie throws, Susie hits, and Billy doesn't hit, then Susie's throw is a cause. Now, it's not a but-for cause. If Susie doesn't throw, then the bottle shatters anyway. But the definition allows me to fix BH at 0. So this is the, let me go back to the definition. I get to choose a set W and fix it at its actual value. So here I'm taking W to be the singleton BH. I'm fixing it to 0, which is its actual value. In the actual world, Billy does not hit the bottle. And if we fix Billy at not hitting the bottle, well, in that case, if Susie doesn't throw, the bottle doesn't shatter, and if Susie throws, the bottle shatters. So we have the but-for causality once we fix BH to be 0. Billy is not a cause. The model is asymmetric. If we fix SH at 0, Well, we can't fix SH to 0 according to this definition, because that's not what happened in the real world. So we're allowed to fix BH to 0 because, in fact, Billy's rock did not hit the bottle in the real world. We can't play the same game and fix SH to 0. The definition doesn't allow that, because it only allows you to fix things to their value in the actual world. And in the actual world, Susie's rock hit the bottle. So, why is Susie a cause and not Billy? Well, duh, because Billy's rock didn't hit the bottle and Susie's did. This is sort of capturing that. So let me stop here. This is stuff, really, the last 5 or 6 slides have been sort of slides I also use in my talk in causality. And now I'm about to get into new stuff in explanation, although I'll have to start out with a bit more on causality. Let me stop and ask if there's any quick questions. Maybe you can unmute.
Maybe a quick challenge of your definition.
Sure.
So suppose you have a train track, and it splits in two, a switch left or right.
Right.
And there's a problem if there's a train on both sides after the switch, because afterwards they come together again and they collide. So one train, there's only one train. He says the switch says go left.
Right.
And now, wouldn't your model say that? And so in the end, there's no collision, because there was only one train. Well, wouldn't your model say that the switch being left is a cause for there not being a collision? Because if you make the switch go right,
there's only one.
There's only one train. Yes, so there are no collisions possible whatsoever. But if I'm allowed to fix values on the as they are in the real world, then I can make this train in 2 places at the same time. If I switch my switch, the train goes right, but I also keep my train on the left. So I duplicate.
Well, so then I would say you have a bad equation, a bad model. Then I would say you have a bad model, because if there's no train that can go on the right because you've kept the train on the left, then in other words, the train can't be. But if the model allows me to fix the train on the left and then intervene, so to both fix the train on the left and flip the switch to the right, and the outcome is that I have a train on both the left and the right, I would simply say you have a bad model, because the model is not correctly modeling the effect of the intervention. The effect of the if I simultaneously intervene to keep the train on the left and switch flip the switch to the right, it is not the case in the real world that you have a train on both tracks. That's just not true. So your model is not, I would argue, correctly modeling the real world. Your condition would have to be that if there's a train there that can go, and then flip it to the right, it'll go to the right.
And what's the difference with the rock throwing, where if I intervene on Susie not throwing, that I'm still allowed to keep Billy, to refrain Billy from hitting, because, well, in case I block Susie in the real world.
Question. Yeah. So really, in a more refined version of this, I consider normality. Does it make sense that somehow that Billy might not hit? And so it is true that the equations are going to be almost like little miracles if they're interesting, because it counters, it goes against the equations to say that Billy doesn't hit despite the fact that Susie doesn't throw. So I would say that I have a whole discussion on normality in the book. I don't want to get into it in great detail, but that I would argue is a fairly normal situation where, in the real world, really, I would have a more extensive model where I would allow situations where Billy doesn't hit. And it doesn't seem so implausible that there are situations where Billy doesn't hit. So you're willing to consider that model as a plausible model. It's not so abnormal. Whereas a model with 2 trains, that just seems very, very abnormal. So let me go on, not because I think your question is uninteresting, but if I get hung up in this, I won't be able to get the explanation part. This isn't, so there's other examples with train tracks that I discuss in my book for what it's worth. But let me keep going.
So there may be a quick question or two.
Sure.
If it's
Sheila had a question. Sorry, I see your hand there, Sheila.
It's okay. I'll postpone until later, or I'll ask you afterwards, because I want you to get through your talk. Thank you.
Okay. All right. I will keep plowing on through. So let me get to. So it turns out there's another flavor of causality that I actually talk about in the book as well, which seems to be more useful for explanation. And let me call that sufficient causality. The basic idea is due to Pearl. So x equals little x is a sufficient cause of phi in a context, just like before. If not only does x equals little x bring about phi in U, but it does so in all contexts. So let me give you, well, here's the formal definition, but I'll give you examples that'll make things better. So just like before that, we have this condition that says, I would never say x equals little x as a cause of phi unless they both happened. Here's the complicated condition. Some conjunct, remember, this is a conjunction of a bunch of things. Some conjunct of x equals x is part of a cause of phi in mu. I've defined what it means to be, it's part of a cause of phi if I can extend it to a bigger conjunction that includes that conjunct, that's a cause in the sense of the previous definition. This will seem mysterious, but bear with me, I'll give you examples. And here's the interesting new clause that says setting x to little x results in phi in all contexts. So that's this, it's enough to make phi happen, no matter what. And then we have this minimality condition. So the action is the new clauses are obviously the second and third clause. The third clause, I hope, is fairly easy to understand. It's saying that if Susie throws the rock, that's enough to make the bottle shatter no matter what Billy does. This would be true if in all contexts Susie never misses. And in general, if you have a conjunction here, so if this was just a single conjunct, this would just say that that conjunct is a cause of phi, right? You can't be a sufficient cause unless you're a cause in the old sense. But in general, I'm going to need extra conjuncts here. And let me explain by example. So I don't want to say the whole thing is, if this is a conjunction of 5 things, I don't want to say all 5 of them together are a cause of phi, because that will in general violate the minimality condition. It's enough for me to say that some subset of them is a cause of phi. Right? There might be extra conjuncts here, and intuitively there might be extra conjuncts to make sure that in other contexts, setting x to x causes phi. So let me say that slowly. The interplay between SC2 and SC3. So when I talked about actual causality, I just worried about the context U. I did not worry about other contexts. So I said, okay, and I have a minimality condition. So I would never say that throwing the rock and sneezing is a cause of the bottle shattering in context U, if throwing the rock was enough to cause the bottle to shatter in context U. On the other hand, suppose, I'd have to come up with a crazy story, that in another context, you needed the sneezing to cause the bottle to shatter. Maybe somehow because Susie sneezed, she threw a few seconds later, and the bottle was protected, but because she held up the throw for a second or two, she managed to shatter the bottle. So that you didn't need the sneezing to cause the Susie's throw to shatter the bottle in the context U, but because I'm now requiring setting x to x to result in phi in all contexts, I might need some extra conjuncts here to make this happen in all contexts. And the extra conjuncts are not relevant in context U, but might be relevant in other contexts. So that's why in SC2, I don't require that the whole big conjunction is a cause. I just require that part of it is a cause, is enough to get a cause. So let me give examples. In the disjunctive forest fire example, actually things work out nicer. Both, either arsonist throwing is a sufficient cause. Right? If either one of them throws, that's enough to get the forest fire to burn down in all contexts, where the different contexts are, who throws, right? In the conjunctive forest fire example, now you get the conjunction, whereas before in the conjunctive forest fire example, each one by itself was a cause. In the context where both of them threw, in the context where both of them dropped a match, each of them by himself is a cause of the forest burning down. But in general, if you look at other contexts where only one of them might drop a match, you need both of them to drop matches to get sufficient causality, because sufficient causality says even in the context where only one of them drops a match, then if both of them were to drop a match, then the forest would burn down, right? Whereas ML1 is not a cause, because in the context where just ML1 drops the match, getting ML1 to drop a match isn't enough to burn the forest down. So for the conjunctive forest fire example, you need the conjunction, and in the disjunctive case, you just need each disjunct, which sort of maybe suggests that maybe we're quite often talking about sufficient causality. So now whether something counts as a sufficient cause depends on the set of contexts. Because here I say, for all contexts U, well, what are the contexts U? That's determined by the model. So if in all contexts, Susie throws and she never misses, then the Susie throwing is a sufficient cause of the bottle shattering. But if there are contexts where Susie doesn't throw, or sometimes throws and misses, then her throwing is not going to be a cause. But her hitting the bottle is a cause. If you intervene and get Susie to hit the bottle somehow, well, it doesn't matter if she misses, she hit the bottle anyway. If either Susie or Billy is always guaranteed to hit the bottle, but maybe in some cases just Susie, or maybe in other cases just Billy, then the conjunction is a cause. You need both of them to throw to make sure that the bottle shatters. So I'm hoping you're getting the intuition for sufficient causality. And the reason I'm doing this is that I'm going to use sufficient causality in the definition of explanation. Now, remember when I talked about explanation, I said it matters what you know. So what counts as an explanation is relative to what you know, and people who know different things will view different things as explanations. So in the definition of explanation, I'm going to have to capture what you know. And the way I capture that is by taking your knowledge. Actually, I have a more general definition, but let me start out with a simple definition where you intuitively know the model. I'm going to assume the model is known. And all you're uncertain about is the context. So you can think of the model as describing how the world works. What are the equations? So I'm assuming you understand the equation. So I'm assuming, for example, you understand in the disjunctive forest fire. I won't go back. In the disjunctive forest fire case, you understand that it just takes one match to get the forest to burn down. You know what the model is. Or in the conjunctive case, you understand that it takes two matches to burn the forest down. That's captured by the equations. So if we assume the causal model is known, I'm assuming you understand the equations, you understand the way the world works. What you don't know is what actually happened. That's the context. For example, which arsonist dropped a match? That's encoded in the context. And your set of possible contexts say, well, it's possible that only arsonist one dropped. Suppose you're a police investigator investigating how the forest burnt down. So you understand that the forest is dry enough that all you need is one match, but you're not sure if arsonist 1 dropped a match or arsonist 2 dropped a match. You are sure that one of them dropped a match because the forest burned down. Maybe there's a third arsonist, so that's your context. And so you can think of K as the set of contexts that the agent considers possible. In shortly, I'll actually put a probability distribution on K, but let me start without it. So I'm going to say X equals X is an explanation of phi relative to a set K of contexts. So this is, what counts as an explanation is relative to your knowledge, and your knowledge is being captured by the set of contexts. And what's the definition? It says, well, X equals X is a sufficient cause of phi in all contexts in K that satisfy X equals X and phi. So let me unpack this. I'm saying, look, intuitively, if you're telling me something's an explanation, then suppose it actually happened. So intuitively condition on the fact that it happened. So we know that phi happened, we're trying to explain it. Let's assume that X equals 3. So in all the contexts, let's just focus on the context where X equals 3. And let's see if it counts as an explanation. So you're conditioning on what you know. We can only consider context in K and SC3. So when I use the word sufficient cause, I have to unwrap that with these conditions, SC1, SC2, and SC3. And I'm going to replace in the SC3 all contexts U. I'm going to replace that by contexts in K where x equals little x and phi holds. So it's not, so when I say sufficient cause, I really should have said sufficient cause relative to k. So just restrict the context in k here. This is where the knowledge is coming in. So back to the definition. So when I say sufficient cause in all contexts in k, I really mean in SC3, you only look at context in k, because intuitively you know that those are the only contexts that arise. That's your knowledge. And again, we're going to assume that x is minimal. There's no strict subset of it that satisfies the x1. And the other condition we have is that x equals x and phi actually happen. You consider possible a context where the explanation holds. You wouldn't call something an explanation if it never happened. So I'm hoping that, so the key point here is sufficient causality. Yeah, sorry, Bart, you had a question?
I don't understand the conditioning. I understand the conditioning on x, but not on phi, because we're trying to explain phi, and then
right. So let's assume that phi holds. So usually, I wouldn't even mind assuming that in k, phi always holds. That is, you've seen the forest burn down. You're trying to explain it. Okay. So intuitively, you know the forest burned down. There's no doubt about it. You wouldn't bother trying to explain something in general that hadn't happened. Right. So in general, when we seek an explanation, I'm making a claim about how people work. When we seek an explanation of phi, we already know that phi happened. That's, you know, we're not uncertain about that. So I would be perfectly happy to already restrict k to contexts where phi happens. This has the same effect.
But that kind of excludes all types of but-for reasoning, because if we're only considering contexts anymore, in which, well, the forest burns down, well, then, well, empty set is a trivial explanation because, yeah, in all possible contexts,
no, it's not.
Consider
so I would argue, no, it's not. That although the first, I mean, go back to the definition of causality. In the definition of causality too, I have an AC1 that says I wouldn't call something a cause of phi if phi didn't happen. So I'm in a context where phi happens for sure. But nevertheless, AC2 is not guaranteed. I know that phi happened, but I'm trying to figure out which of the many other things that happened caused phi to happen. So I would say the same thing even more strongly in the case of explanation. If we're trying to explain the forest burning down, we know the forest burned down. We're trying to figure out which of the other things that happened explains the forest burning down. And it's not trivial, even though I know the forest burned down, it doesn't mean that the empty set is a cause of the forest burning down. That's false. That because the empty set wouldn't satisfy the conditions of sufficient cause. Right. I do have a minimality clause, but the minimality clause wouldn't work. It wouldn't satisfy the counterfactual, for example. So if you go back to SC1, SC2, and SC3, I could take X to be the empty set. That would be the but it wouldn't satisfy these three conditions if I did. Well, it would satisfy the first one. This is trivially true, but it wouldn't satisfy the second one. And it for sure wouldn't satisfy the third, because phi might not hold in all contexts if you didn't do anything.
But so, phi holds in all contexts since you conditioned on that, right? So SC3 would
say that provided X equals little x happens, then phi holds.
Yeah.
So if X is the empty set, SC3 would only, okay, you're right. In this case, if I take K to be just context where phi holds, then this would hold in all contexts. But this would.
It's SC2, okay.
Yeah. And actually, I think in the book, I didn't restrict, I didn't assume that K consists of all contexts for phi holds, but I don't mind. So it turns out that this will work no matter what. All right, now let's get to some examples just to give you some intuition. So in the disjunctive forest fire example, let Uij, this looks like it's notation heavy, but it's actually easy to read. So suppose the context determines whether or not the first arsonist drops the match and whether the second arsonist drops the match. So U00 would be neither one drops the match. U01 would be the first one doesn't, the second one does. U10 is the first one does, the second one doesn't. And U11 is the context where they both drop the match. I hope that's clear. So I'm saying there are four possible contexts depending on which of the two arsonists drop a match. And if you have no idea who dropped the match, then in the disjunctive case, both ML1 and ML2 explain the fire. Each one of them is a sufficient cause, right? So we get that. It's minimal. The empty set is not going to be a cause. And there is a context where if we consider all four contexts, there is a context where the first one drops a match and phi happens, and there's one where the second one drops a match and phi happens. So it's fairly easy to see that and I hope you agree it's reasonable that either, what's an explanation of the forest fire? Well, saying that the first guy dropped a match is an explanation. Saying the second guy dropped a match is an explanation, because you know that the model is such that all it takes is one match, right? On the other hand, if you already knew that the second guy didn't drop a match, that's what this is saying, that you consider it possible that neither dropped a match or that the first guy dropped a match, but you don't consider it possible that the second guy dropped a match. Then saying that the first guy dropped the match is an explanation, because now you intuitively know that you're here. But saying that the second guy dropped a match is not an explanation. EX3 fails. EX3 is the one that said you have to consider possible a context where the explanation holds. Well, you don't think it's possible the second guy dropped a match. You know for a fact he didn't. That's what K is telling you. So saying that the second guy dropping a match explains the forest fire doesn't count as an explanation if you knew who didn't drop the forest fire. I mean, again, I'm sort of hoping in the real world, I mean, I'll forget my formal definition, it seems right to you that we would not accept the second guy dropping a match as being an explanation of the forest fire if we know for a fact he didn't drop the match. That's just not a good explanation. The first guy dropping a match is an explanation. You didn't know that you thought it was possible he dropped the match. You weren't sure. And that's why you thought both of these were possible. Now, if I tell you he did drop the match, that works. Now, in the conjunctive forest fire example, I need them both to drop the match for a sufficient explanation relative to complete uncertainty. I have no idea who dropped the match. On the other hand, if I already know, if I know that this is just saying, I know the second guy dropped a match, right? Because in both of these contexts, the second component is one. The second guy dropped a match. The first guy, I'm not sure. So saying the first guy dropped a match, that counts as an example in the conjunctive case. I already know the second one dropped the match, right? So that knowing the second guy dropped a match, it's enough to know that the first guy dropped a match to explain why there's a forest fire, because it takes both of them to get a forest fire. The conjunction is no longer an explanation because it violates minimality. ML1 is already an explanation. I already knew that ML2 was 1. That was part of my knowledge. You don't have to include that as part of the explanation. And likewise, telling me the second guy dropped a match is not an explanation. I'm uncertain about the first guy, so just knowing the second guy dropped a match doesn't explain in general why there's a forest fire. And similarly, if Susie always throws and never misses, then the fact that she threw explains why the bottle shattered. So if you know in general she always throws and never misses, then her throwing explains the bottle shattering. All right, so that's the key definition of causality. I want to spend the 10 minutes remaining, and I think I do have 10 minutes in the talk part, right? Until 11:20. An issue that arises with explanation that didn't arise with causality is that not all explanations are equally good. So we want to talk, I mean, we do talk in natural language about this is a better explanation than that. And I want to try to make that precise. And the trouble is there are many dimensions of goodness. An explanation is better if it's simpler, if it's more general, if it's more informative. We can get into what these words mean. I'm going to focus on 3 types of goodness. And the problem I'm going to get is, explanations are going to be incomparable. You might be better in one dimension and not better in another, right? So that's where I'm headed. So let me, so going back to the definition, EX1 appeals to sufficient cause and thus requires SC2 and S3. These are the conditions for sufficient cause. And it's basically saying that U has to hold in all contexts. The SC3 part says that U has to hold in all contexts in K, right? So it is relative to my knowledge, but What happens if these conditions don't hold for all contexts, they only hold for most contexts? And this becomes particularly interesting if I have a probability on contexts. So most here means they hold with high probability, taken with respect to my distribution over contexts. So imagine that I had not just a set of possible contexts, but a set of contexts associated with a probability, right? Standard probability on context. And then I can talk about how good an explanation is. I can make that precise by saying, with what probability does SC2 hold? With what probability does SC3 hold? So SC2 and SC3, let me quickly remind you, because you surely haven't memorized these. So S3 says, for example, once I said x to little x phi holds in all contexts in K. And so Bart, for this to make sense, I would have to allow contexts in K where phi might not hold. But maybe it holds for most contexts. Or similarly, for each context U and K, maybe x equals little x, or part of it is not a cause, but maybe it's a cause in most contexts. So I can quantify that by saying, what is the probability of the set of contexts for which SC2 holds or for SC3 holds? So I can talk about an explanation has goodness alpha, beta. Alpha and beta are both numbers between 0 and 1. So think of this as being 0.9 and 0.7. If SC2 holds on a set of contexts that has probability at least alpha, and SC3 holds on a set of contexts that has probability at least beta. So all I'm saying is, whereas SC2 and SC3 require a property to hold in all contexts, I could weaken that and say, well, it holds in almost all contexts where almost all is defined by alpha beta, right? So that's a sense of how good you are. Clearly, the higher alpha and beta are, the better an explanation it is. So let me give you an example. And I claim that people actually think this way. So here is an example. So, the disjunctive forest fire example, did I not have it? Oh, here's my example. Sorry, I skipped the slide. So suppose Victoria's tanned, and I seek an explanation. This example is actually a variant of one used by Peter Jardenforsch. So the causal model includes 3 variables. Victoria took a vacation in the Canary Islands. It's sunny in the Canary Islands, and Victoria went to a tanning salon. So there are 8 contexts assigned, saying yes or no. Victoria took a vacation in the Canary Islands, yes or no. It's sunny in the Canary Islands, yes or no. She went to a tanning salon. So that gives you 8 different contexts. Now I claim Victoria going to the Canaries is not an explanation. It doesn't satisfy SC3. SC3 is the one that said, well, if she goes to the Canaries, if you intervene and make her go to the Canary Islands, then she'll definitely get a tan. Well, there might be a context where she doesn't get a tan, because although she went to the Canary Islands, or if you intervene and give her the plane ticket and get her to go to the Canary Islands, it's not sunny. That's unusual, but because it's not sunny, she doesn't get a tan. Or it might not satisfy SC2 that going to the Canary Islands was a cause of her getting the tan, if the reason she got a tan is that she went to the tanning salon. She actually went to the tanning salon before she went to Canary Islands. So even though it's true that she has a tan, the cause of her getting the tan is not her going to the Canary Islands. That can happen, right? The cause is that she went to the tanning salon and she was already tanned by the time she went to Canaries. She got on the plane with a tan, right? Now you might say that these are very unlikely scenarios. Fine, have your probability distribution, make those scenarios unlikely, no problem. And then people would accept Victoria took a vacation to Canary Islands as a satisfactory explanation, although you can think of scenarios where it doesn't satisfy SC2 and SC3. That's what I gave you here. So, formally it's a partial explanation with high alpha and beta, provided you give these scenarios low probability, right? So let me not go into the formal details, but I hope you can sort of get the picture that you have a bunch of contexts in mind that tells you how things are going to play out. And there are contexts in which SC2 and SC3 don't hold. So technically it's not an explanation, because the definition of explanation, EX1, requires, it requires it to be a sufficient cause, which means it has to hold in all contexts, but it might not, right? But if it holds in most of them, you'd say, that's a pretty good explanation. And this happens all the time in science. right? We try to explain certain phenomena in science, and we realize there's scenarios where our explanation doesn't work. But we still say that's a pretty good explanation. It seems to cover most scenarios, right? And that's what this is trying to capture. So it's one flavor of goodness. We might prefer the more likely explanation. That's different. So in disjunctive forest fire example, suppose I give U01 a higher probability. Remember, U01 is a setting. Oops, I think I have this backwards. There's a typo here. The setting where the second arsonist drops the match, the first one doesn't. So if I give what I really meant to say here, there's a typo. If I give U10 higher probability than U01. So I give the scenario where just the first arsonist drops the match, higher probability than just the second arsonist dropping a match. So that's not what it says here, but pretend it did say that. This is a typo. Then I would call ML1 equals 1 a better explanation of the forest burning down. There should be FB, there's another typo. You can tell I'm giving this talk for the first time, so there's still more typos than I'm happy about, but it's a better explanation, not in this sense. It's a better explanation in the sense of it has higher probability, higher ML being 1, let's say you believe it's more likely the first guy drops a match than the second guy. It's ML1 being 1 is a better explanation of F equals 1 than ML2 equals 1, because it has a higher probability. So this is another notion of better explanation that, again, I claim we use in the real world. Something is a better explanation if it was more likely to happen, right? You don't know a priori which guy dropped the match. You think that the first guy, I mean, what the police do all the time, they don't know who robbed the bank, but they have a list of suspects that they think are more likely than other people. There are better explanations for the bank being robbed. And again, it's different from this notion of partial explanation. It's just another notion of goodness. I'm not talking about better or worse, it's just different. In the disjunctive, so suppose there's a fire in the lab and you suspect an arsonist. So now I'm going to give you a bad example where likelihood doesn't seem to work. So suppose K consists only of contexts where there's a fire. So for a fact there was a fire. And suppose that O equals 1 just says there's oxygen. So O equals 1 is a sufficient cause for a fire relative to K. That as long as there's oxygen, there's going to be a fire. And you're almost certain that there was oxygen in the lab. It's just really unlikely that somehow the lab was emptied of oxygen, although I guess it's possible. But we don't view the presence of oxygen as a very good explanation of fire, although it has high prior probability. So in this sense, it's a good explanation. So there's a third notion that I want to talk about of goodness of an explanation, and then I'll stop, Bart. I'm really almost done. So roughly speaking, we define the explanatory power of a partial explanation as the probability of phi happening conditional on X equals X. So oxygen being 1 has low explanatory power because conditional on there being oxygen, it's highly unlikely that there's a lab fire. Just having oxygen in the air doesn't make a lab fire very likely. I certainly hope not. This rough definition is not quite right. So this is actually not the definition I want to use because it confounds correlation with causation. It would say that a falling barometer would have high explanatory power for rain, and we don't want that to be the case. So we define the explanatory power of X equals X relative to phi as the probability that X equals X is a cause of phi, conditional on X equals X. So it's not the probability of phi happening, it's the probability that X equals X cause phi to happen. How likely is that? So that's the definition of explanatory power. And I should say that I've given you 3 notions of goodness. There's a tension between them. They're different. You can have one and not others. No one implies the others. And I don't think there's a right answer of what counts as a better explanation. You have, if you like, a partial order in explanations. Some are better partial explanations. They hold in more context. Others have a higher a priori likelihood. Others have higher explanatory power. And you just have to decide what's important. So the message I want to leave you with is that there are different metrics of goodness of an explanation, and there are others. I don't want to pretend these are the only 3. And that's a partial order, and there's no sort of right answer of what's better. And I just want to talk about one more thing briefly. Remember, I said way back that one explanation for Mr. Johansson's lung cancer was asbestos causes lung cancer. And that explanation can't be captured by an explanation of the form X equals 3. Basically, a more general notion of an explanation is me saying X equal 3, and me telling you something about the causal model, like if there's asbestos, you'll have cancer. And that's the psi. It's a statement about the causal model, and I've run out of time, so I can't go into technical details, but there's a definition of, I extend the x1, x2, and x3 to then take the psi into account, roughly by saying, adding this clause, so now I'm going to allow my uncertainty not just to be over the context, but to be over pairs mu. So I might be uncertain not just about what happened, but how the world works. So up to now, I've been assuming that you knew the M, you knew the causal model, you knew that in the disjunctive forest fire case, dropping a match was enough to cause the fire. Dropping one match was enough to cause the fire. Here I say you might be uncertain. You might think, well, maybe it needs one match, maybe it needs two. So now your K, the set of things you're uncertain about, really consists of pairs mu. You're not just uncertain about who dropped the match, you're uncertain about how many matches it takes to cause the fire, which means you're uncertain about the equations, which means you have more than one causal model in mind. So now in general, you're going to have a probability on pairs mu, where M is a causal model and U is a context. And the psi says you restrict to M's that satisfy this formula psi. So you're only going to be interested in causal models, for example, that satisfy this equation. And then we can get analogs of the conditions in this more general case. All the notions of goodness apply in the more general setting. I've run out of time, so I won't say anything about that. So just let me conclude that explanation is a slippery notion. The definitions I'm giving you here weren't the first or second that I tried. They really were more like the 7th, 8th, or 9th. And it's not even the definition in the original paper I wrote with Uta Perlin explanation. I'm focusing more on sufficient causes. I now think that's better. It's not clear how to prove a theorem saying you got the right definition. And I've just scratched the surface. There are many notions of goodness. I hope that was sort of clear. The modeler needs to trade them off. And if you want to know more, here's a shameless plug for my book. I have a whole chapter on causal explanation in chapter 7, but all you really need to do is read chapters 1, 2, and 7. You can skip all the rest if you're interested in explanation. So let me stop there, allow some time for questions.